Hi, this is Mike Olbrys from Professor Castel's Calculus 1 class, Macomb Community College. Today we're going to be doing finding extrema and inflection points based off the first and second derivatives. For this particular question, it also asks for the roots, so here I started with the function from the review. It was f of x equals x cubed minus 15x squared minus 33x. Factored out x, and then I had to do the quadratic formula for that bottom, or for the other part, and that's what the quadratic formula is there. And the roots for this problem are 0, where is it? 0. You solve all that out. The roots are 0, 16.9, and negative 1.94 after you solve out that quadratic formula. And then the 0 is from the x that you pulled out when you factored it originally. And then for the relative extrema, or the minimum and maximum, relative max and mins, you take the first derivative of the original function. So I would go with the unfactored form because it's easier. You take the derivative of that, that's going to be 3x squared minus 30x minus 33. That's going to be the first derivative of the original function of x cubed minus 15x squared minus 33x. Now you got that, you gotta do a little factoring with that, so we'll pull out the 3 to give you x squared minus 30x minus 11, or not 30x, I'm sorry. When you pull out the 3, it'll give you 3 times the quantity x squared minus 10x minus 11. And then you factor out that quadratic there. That's going to be x minus 11 times x plus 1. Alright, so that's going to be the factored form of the first derivative. And then you have to determine where the f prime of x equals 0 and where it does not exist. So for the zeros, f prime 0, it's going to equal 0 at 11 and negative 1, because if you plug those values into the derivative, you will get 0. And then you have to also see if it doesn't exist anywhere, in which case it wouldn't have any relative max or min, it would just have a critical point there. And since it's a polynomial, it exists everywhere, so we don't have to worry about it not existing anywhere. So you get those values, 11 and negative 1, for where it equals 0 at the derivative, and it exists everywhere. So then you're going to make a sign chart with those values, 11 and negative 1, to find where the max and mins are, if there are any in the function. Three is going to be positive everywhere. X minus 11, it's going to be negative for any value that's less than negative 1. For the values between between negative 1 and 11, it is going to be negative as well. And for anything higher than 11 will be positive. And then for the factor x plus 1, anything less than negative 1 is going to be negative. And then it's going to be positive between negative 1 and 11, and positive for anything greater than 11. So your sign chart will look like this. And it's going to be positive to negative to positive. That's what f prime is doing. So f is increasing when it's less than negative 1. It's decreasing when it is between negative 1 and 11. And it is increasing greater than 11. So there's going to be, so negative 1 and 11 are both critical points, and when it goes from increasing to decreasing, you're going to have a max, and when you go from decreasing to increasing, that is a min. So max at x equals negative 1, and the min at x equals 11. Alright, there's the bottom of the sign chart there. Increasing at the interval negative infinity to negative 1, decreasing from negative 1 to 11, and increasing again from 11 to infinity. So you got a max at negative 1 and a relative min at x equals 11. Now, problem also asks for inflection points, so you have to take the second derivative in order to do that. So we have the first derivative as, the first derivative was 3x squared minus 30x minus 33. Take the derivative of the first derivative. It's going to give you 6x minus 30, it looks like. Yep, minus 30. Factor that a little bit. Take out a 6. You're going to get 6 times the quantity x minus 5. And then again, you have to find where f double prime of x equals 0, and also where it would equal, where it does not exist. Alright, so it would be 0 if you plugged in 5. So x equals 5. And it exists everywhere because, again, it's a polynomial. Single power. There's that. Take the derivative there. Get 6x minus 30. And then you factor out the 6. And see that 5, if you plug in 5 to that second derivative, it'll be 0, and it exists everywhere because it's a polynomial. Okay, so then you gotta make another sign chart for this one. This one's only gonna have one value, it's 5. And the factors are 6 and x minus 5. 6 is positive everywhere. X equals negative 5. Anything less than 5 is going to be negative. Anything greater than 5 will be positive. So you're going to have a negative and a positive. So there is an inflection point at 5, at x equals 5 in the original function. So because the first before 5, it's concave down, and after 5, it is concave up. When it switches concavity, there's an inflection point. So, inflection point at x equals 5. There's that sign chart there. Put the 5 on it. The factor 6 and x equals -5. 6 is always positive. Less than 5 would be negative. Greater than 5 is positive. You should go, the second derivative is negative for f, or less than 5, and then it's positive greater than 5. When you go from, when you switch concavities, there's an inflection point. The inflection point is that x equals 5.